Is that
Yeah, but you better prepare.
so you and I will be back. So today we'll look at some mechanisms for actuators, particularly a lot about gears. And there's another version of gears that doesn't have any teeth, the gear teeth. You'll be able to see that it comes in different shapes like cams. So if you have not heard about cam before, you get to see what it is today. Now for the gears, we'll be looking at a few types of gears. There's one type that's called simple train. The simple train is just cascaded gear on different shafts. There's another type that they share the same shaft. So we call that compound gear train. And the reason for the gears is because we want to use gear as a gear reduction. You may have heard that before, reduction gears. So I'll share with you a little bit of insights about reduction gears. Why do we use reduction gears? And there's going to be another kind of gear version where you have one side that's a normal round gear and the other side the gear is like a straight line. So that straight line gear is almost like a gear with a infinite radius. So if there's a gear that's infinite radius, if you look at one section of it, it's kind of like a straight gear. So that one is called translational gearing motion. You may have heard about ratchet. So we'll just share a little bit about ratchet and wrap it up by talking a little on bearing. You see that this preparation is just in one lecture. Your mechanical design engineering friends, they will learn a lot more about all these gearing systems. So in order for you mechatronics to be able to kind of like be friends with them, you got to learn all this terminology. Go to them and say that, hey, I learned helical gear today. And they look at you, yeah, you sound like an intelligent guy, I want to be friendly with you. So I'll have an animation about helical gear. This is quite a difficult concept to understand. Okay. So now you find that in your FYP, I kind of try to always relate to your FYP. I know there are different types of FYPs out there, but a lot of you through your FYP may be considering, hey, I want to do some kind of measurements. You may be thinking about sensors. And after you sense something, okay, now I want to make things move. If you want to make things move, then you need actuator. So this sensor and actuator topics, actually, I heard from your alumni seniors, they came back to me and said that your lecture, Dr. Tan, your lecture is one of the lectures that's very useful to me when I start working. And I can appreciate why, because sensors, actuators is all around us. So even though we touch just very, very, very little topics in all the different actuators and sensors, but a lot of these are commonly used, so they'll become very useful. And in actuators, we'll be looking a lot about mechanisms. If you're in a full mechanical degree program, there's a whole lot of, there's one full module just talking about mechanisms of machines, and just focusing on that. Over here, we only got a couple of slides. So it's really, just a very introductory form. So the next couple of slides, you get to see a lot of definitions. Mechanisms transform one form of motion to some other. So basically, that's a definition for mechanism. To give you some idea about some examples of mechanisms, you can think of linkages. Linkages are just like a series of joints, kind of beams that are joined together, where one of these beam, we don't call it beam anymore in robotics, we call it a link. So later on you get to see some of this definition. Cams, later on I'll show you how it looks like. Gears, you'll find them, most of you would know what is gear. Rack and pinion, some of you may have heard before. We actually didn't do much, we're not going to be doing much about chains or belt drives. But these are some of the mechanical elements that you can find. If you have got friends in MDE, they actually got a module that I used to be teaching them that's called Microelectronics in Consumer Products. Yeah, that was just over. Some of them may have approached you before. At that time when I was teaching them, because MDE, they are wondering, why do I need to learn electronics? Why do I need to learn all this? I'm mechanical, you know? Yes. But there's something that you didn't know. All mechanical components these days has to be controlled electronically. Yeah. Gone are the days where computing speed isn't fast enough, so it becomes expensive to control mechanical components. But these days, super cheap. Arduino, the one that a lot of you are using. How much is that? $40?
Depending,
Yeah.
you buy from where?
That's 5 cheeseburgers. Depends on what size you get. You can afford to buy that off shelf and start playing with it. It can do a lot of things with microcontroller. So we use that to control the mechanism. So mechanism still has a role in mechatronics, robotic system. Some of my FYP students are using a lot of that already. They provide functions like force amplifications for the mechanism. So that's something that electronic products wouldn't be able to do, because there are some mechanical advantages that you can derive out of mechanisms. And we also use mechanism to change speed, transferring rotation from one sharp axis to another sharp axis. And I want to show you this video about this quick return mechanism. And when you see this quick return mechanism, I want you to think, what are the possible, or what kind of real life examples you have seen before that uses this quick return mechanisms. This is how it looks like. So there's this returning side, and there's this actuation side. Sometimes just called the cutting angle, this top part there. So there's no motor over at, could you see my cursor? No, yeah. Could you see my finger?
Nope. No.
Okay. So there's no motor over here. This is the one that has an actuator that moves this linkage around. And there's sort of like this link to that link. There's also no motor at that part. And this thing is pushing it along in this horizontal direction. So some of the FYP students were asking me, how do I get linear motion out of something that's rotating? This one. So if you want to move something straight forward, this one possible mechanism. Just purely mechanism. Using mechanism to achieve the goals that you want. Something that electronically you couldn't do. So these are some examples. So any real life scenarios that you can think of that uses this quick return mechanism. Now, why is quick return? That was because Yeah, you can see that the bottom part here, returning angle is a lot more smaller than that cutting angle, that forward propulsion angle. So it moves slowly forward and then quick return and forward again. So any example of that you can think of?
Rifle.
Like what?
Rifle. Rifle.
Rifle. Quick return mechanism. Yeah. You mean like after firing and then you have something the return of your, we used to call that the bolt.
The bolt.
The bolt. Yeah. I was using M16 during that time.
I use both.
And yes, you have it. Yeah.
Yes.
So, but that one is using the air mechanism, not really a physical link kind of a mechanism, but it has some quick return. Yes. You can imagine maybe in a production line if you need to use. I'm not sure. Do you do woodwork here? There's this thing that's called planing, where you shave off the layer of the wood. So that shaving off of wood, yeah, you need that slow forward motion and quick return, and doing that sort of shaving. So for grinding, for shaving, all this sort of production work, you can use this quick return mechanism. Now, just a few more definitions that I want you to know. Things like link. Yeah. Link would be one of this arm that you saw just now. All these are linked. And if you have two links that kind of like connected to each other, just like my arm, this one link, and this is another link. Right. So that point over here. It's not called connector, but in robotics terminology we call it node. So this is a node. And some students wonder, why isn't it called a joint? In English word we call it a joint. Because in robotics, a joint is when you have more than one link that's connected to that node. So if you've got a few other links that's connected to that node, then you call that a joint. So that's also written over here. Two or more links connected to the nodes. So just some terminologies. So you can see that if you have a series of these links and joints, will form up your kinematic chain. An example of a kinematic chain is what you could see in a turbine engine. You may have seen some videos before how the V6 piston in the combustion engine works. That it has some precisely timed movement, both to inject your fuel, and the other one is to take off the exhaust. So the timing has to be very precise. So what is actually happening is that there is this is not quite exactly what you can find in automobile, but the principles are more or less the same. So it has, again, this part here that's rotating, right? A rotating disc. So we can simplify this rotating disc to just a link in that way. So there will be a link from this center part of that rotating disc joined to this other part of this link. So there's one, which is your crankshaft. So crankshaft is where you have the shaft part that controls the timing of all these linkages. So this part number 2 is called connecting rod. Connecting rod. And this part number 3 here is actually a fixed frame. So your crankshaft over here is rotating with reference to a fixed frame. And then the last part, that is your piston over here. So the outer shell to the piston is actually called a cylinder. So sometimes you get to hear cylinder as a word to also comprise of piston that's inside. But together you have the piston and the cylinder. So over at this corner is the spark plug. The spark plug job is to provide spark. That's all it does. But it's just not producing spark anytime, but it's timed precisely. And at some precise timing for the spark plug, it would spark and combust the fuel that's contained inside the piston and the cylinder. So you could imagine as this rotates, it will give you that motion of quick return, a forward motion and then a quick return. It will give you that motion as well. I have a video to show you what's going on inside the combustion. An incredible footage.
So this one over here is where fuel will be injected, and then there's another one over there that will take in all the exhaust, and then this one is a piston that's coming up. Bang, right? The spark plug ignites it, and then your piston will energize your car. So I think this one is the exhaust that's going up. So once the exhaust has returned, piston came up. That's the other way around. That's the fuel that was injected. And then the fuel is injected and then compressed, and then the spark plug will ignite it. So this part here is the fuel that's injected. There's another one that uses, instead of 2 valves, because they didn't show the exhaust yet. So the other cycle of it will be that after it's combusted, that as the piston comes back, another valve will open for the exhaust to go up. So all these are timed in a fraction of a second. So you can imagine the timing of your spark plug. You got to be able to respond to that. So this other video just show you one valve, because some engineers thought instead of 2, one for fuel, one for exhaust gas, why not just have one valve that's both for your fuel and for the exhaust? So there's another video that I found. This one. So it's a little bit clearer. So the piston is coming up. You can see that air is being compressed. It's actually a fuel that's being compressed. So the sparking is only for an instantaneous moment, and once it explodes, the piston will move to drive your car. And then now the exhaust, right? After being combusted, all the fuel will turn into mostly CO2, and that will be removed via the same valve again. Fuel that's coming in, and then a spark plug. Come back in to compress that, and then ignite them, and then pushes it again, and that cycle will just continue.
So you need mechanisms, you need microcontroller for this sort of things, because it happens in a very short moment of time. So if you're wondering about the valves, because in this figure there isn't any valves that's connected to it, how does the valve works by going in and out at the perfect timing? Is it that we place another quick return mechanism over there to actuate the valves to go in and out? It's actually not here. Your valve is actually spring loaded, and you have another shaft over here. That shaft will be profiled in certain patterns in order to, as it rotates, it's going to push your valve in and out at certain very precise timing. Try to be able to sketch. Some of this shaft looks something like this. It has this section that's that way, and another section that is like, way. And then another section with a different profile. So all these are called cams. These are called cams. So the cams will be rotating, and you can see that if I have anything that's pressed against this surface, like a valve, as it rotates, the valve will be pushed in and out as it follows the profile of this cam here. So because it's spring loaded, so this valve is always pressing on this surface. So if I look just at this part of it, that is on your next slide. So you have this part here that's connected to that valve, and the cam over here is going to rotate. So as it rotates, it's going to generate this upward and downward motion of this, what we call the follower. So this one is going up and down as a follower, and then this egg-shaped thing, that is your cam, and this is the center of the shaft. So you could imagine that if the shaft is built in this way, where you have different cams that's mounted on it, isn't something going to tell you that as you rotate it, it's going to vibrate a lot because it has a little bit of off-center. So that's where the brilliance of engineering comes in. When we have to make a calculation, how much overall offset do you have to one side so that you can design the cam to compensate. So that overall, as it rotates, your entire crankshaft does not vibrate. So it's actually possible. It's actually possible. You gotta design it and balance it out so that you don't have an overall excessive vibration due to this amount of offset. Where's the offset? Had it been just a circle in this way, if you rotate this shaft at high speed, no problem. But had it been a little bit that way, the center of it is a little bit off. If you rotate the shaft that's that way, you're going to experience a lot of vibration. So the cam is just like that. It's a little bit off-center. Why is off-center? Because it needs to provide this upward and downward motion as this thing rotates. So the spring that's loaded over here continuously press your valve on against the surface of your cam. So it's always touching your cam. So then that leads on to the part about, sounds like the profiling of this cam is very important. If it's a pure circle just like this, and if you put your valve against it and press against it in that way, and then this shaft will rotate, then actually your follower or this valve does not move at all. It's only when you have a cam shape, then it will move up and down in that sequence. So this is a timing that's been provided for your valve to open at the exact moment. Time it with the spark plug to spark that fuel for combustion. So it's a very intricate thing that's going on in there. If your cam were to be rotating in the clockwise direction, so this direction indicates a clockwise direction, you can almost see that if you start from here, right, that means the egg shape is going to be kind of like in that way, right? If you start from there, it's going to go through that motion before it will experience this rise part of it. So that's why this is called rise. Now why is it rising? Because your blower will be moved upward as this cam were to rotate. So in this position, that is its maximum displacement toward this direction. So that part here constitutes the rise direction. So you can almost see that the rise comes about because at various angle, you can see that length increased, right? So the length got longer and longer, and that translates to the motion of this valve that's going upward. And as it goes on to the other side over here, you can see the length of these lines here becomes shorter and shorter. So that's where your follower starts to come down, and this portion here we call it the fall. So there's a rise and a fall. And then it goes into this other side over here. You can see that it's a constant radius. So this is what we call the dwell, right? So a dwell is necessary because you need the valve to be kept in order for combustion to happen. So there is this timing of opening, closing, and wait. Open, close, wait. This sort of timing. So we can make use of the various designs of this cam to come up with various different profiles. So a profile that is of this nature, maybe if I start here, start from here, let's see, yeah, maybe start from that way, this egg shape. Alright, and call this position as my 0 degree angle position. So I can start to measure at certain degrees angle, it will give me certain displacement. And I'll get a certain curve, a certain profile, how the follower is going to be moving up or down. So we can do this kind of plot for any kind of cam shape. So one example is this cam shape over here. This is a very popular one. It's called a heart-shaped cam, and it's hard for you to see why this thing would be a linear line. But actually, if you do the measurements of that, as it goes to this part here, that is when it's over here. So in this angle, it's called a 0 degree angle, and then you move through by rotating clockwise. You will move through that, and then you will achieve that straight line, and then that will be the rise. So over here will be the rise, and then over here will be the fall. Right? So there will be different profiles for different kind of cam shapes. Another popular one would be the pear shape. So it's surprising that a heart shape will give you a straight line, but you would have thought that a pear shape is the one that's going to give you a straight line. But actually the pear shape will give you this sort of profile. Right? So you have these two types of profiles, the heart shape and the pear shape. So you could see that the pear shape, this part of it, is mostly in the dwelling state. This part of it is mostly in the dwelling state. And that's why you have this displacement here, more or less about kind of like straight. Yeah. So when I was learning about cams, it actually went into a great level of detail. Yeah. You could imagine that after I'm able to sketch out that displacement profile, I'm able to use the displacement profile to derive velocity by differentiation or integration. Differentiation. So if you differentiate ds over dt, that will give you velocity, right? So if you have your displacement profile, by differentiating that, then hence you can get your velocity profile. Velocity profile of what? Velocity profile of how your follower is behaving. So that linear motion, you will know how it will displace, how much it will displace, how fast it will displace. You can derive from that profile. You would also want to know the acceleration of this linear motion of your follower. So what you need to do next is to differentiate again your velocity profile to get your acceleration profile. Why are all these things necessary? That's because if you were to have sight of your acceleration profile, it would tell you, is your cam that you have designed giving you a smooth response. How do I relate that? That's because for your follower that's following your cam profile, had your cam profile not been in the right kind of profile such that there's a change, an abrupt change of acceleration, you can imagine that your follower is going to knock on your cam. How is this possible? You can imagine that egg shape. If I didn't profile it nicely such that this egg shape is going to be very steep, a very super elongated egg. As it rotates, you can imagine when it comes to fall, it's going to fall suddenly. Right? Fall suddenly means an increase in your acceleration, which in your profile, you'll be able to spot it out. So you can't really design your cam in any other shape that would introduce acceleration, an abrupt acceleration. If you design it in that way at certain rotational speed of that crankshaft, then you're going to experience knocking. So knocking is bad because it's bad for the cam, but then your timing for your valves is going to be off. Right, so there's this intricate design criteria that will go into this car engine cam design. I know that there's this enterprise innovation hub in SIT where recently they organized this Suzhou trip, Beijing trip. It's called Enterprise Immersion Program. So I went for that Suzhou trip, and I know that previous years they actually visited a car manufacturing company. So had it been that I didn't get a chance, I visited other industry. But this is one of the interesting things to see that how they go about designing that camshaft. That one single shaft gotta be hardened, gotta be treated so that it will not deform. So because it provides the very critical timing to give you a smooth ride as the engine starts and combusts. So the greater the dwell time, the more the petrol and the air mixture can enter a cylinder. So these are some of the characteristics that are necessary. I want to touch on another thing that we can use to provide timing. That is your gear system. In your upcoming robotics lab, I want you to make use of these principles that you have learned in sensors and actuators. In fact, you'll be asked to write report, I think in groups of 6 or 5 or something like that. In this report, please relate to what you have learned in the lecture. Because when you build the Lego, you'll be asked to build, you'll be building it in a certain way. But it's not trial and error way. It's this knowledge that you gotta apply. You'll be talking about gear ratios, for example. Why did you choose this smaller gear to a larger gear? What kind of gear ratio will you derive out of it? What sort of torque is it applied when you design that gear ratio? So you need to present that sort of calculation so as to not design it by chance just because it moves, but you know that as it moves, what kind of rotational speed, what kind of torque that's being applied. Why is this necessary? That's because in your lab, as you build that robot, it's a lab about robot war, so you build robots to fight each other. So you need to understand how poisonous is your blow against your opponent, how much damage you're going to make. So by doing some of these calculations, it allows you to determine how you can best go about designing your robot. So you need some understanding, at least for the basics, things like for gears. So in gears, you need to learn some terminology. If you have 2 gears, one smaller and one bigger one, this smaller one is called a pinion gear, and the larger one is called a spur gear. The fact that we want to use this gearing system, that's because we want to achieve certain speed and certain torque. Later on, we'll touch a little bit more about the various speed and torques that you can derive out of the different gears. Most of the time, you can see that the gears are arranged such that the shafts are not a common shaft. In this case, these two gears, they would use two different shafts. Right? These two different shafts are actually parallel to each other. If they are not parallel to each other, but perpendicular to each other, then that kind of gear will be called bevel gear. And later on, there will be a diagram to show what is a bevel gear. Now, this spur gear sometimes also called crown wheel, right? Because that's the bigger one, so that's why they call it a crown gear. And for the different gear systems, I think, yeah, okay. This next slide shows you different types of gear systems. So you have the spur gear system, the pinion, and the spur. And then you have this bevel gear where I was talking about the axis. They are perpendicular to each other. Right. So they are perpendicular to each other. So we have a bevel gear. You have, I think, in your Lego set, this even this worm gear over there. Worm gear. So the way worm gear works is that this part here will be actuated so that your spur gear over here would rotate. That brings about the terminology of the input or output, or actually in gear system, we use the word driver or driven. So in this case, for the worm gear, which one do you think will be the driver, the top or the bottom? Yeah, can the bottom be a driver? Yes. Can you drive by rotate? Can you drive this worm gear at the top by rotating this? There's no way. There's no way to do that. The fact that this spur gear can rotate, that's because this one's rotating. So actually, this worm gear system is excellent for the self-locking mechanism. So if you have this part here that's winching, for example, the lift by rotating your worm gear, so you can turn slowly and lift up whatever object. And once the worm gear were to stop, then you will lock this load in place. Instead of a two spur gear where you need to apply a physical brake to it. So worm gear has got that kind of advantage. One problem of this gearing system, for example, spur gear, when the mechanical engineers decide that they discover one big problem. They find that under very high speed, this spur gear system produces a lot of noise. In fact, sometimes it would vibrate under high speed. So if you think about it, taking that microscopic view, when these two gears, spur gear, start to mesh and touch each other at the teeth, do you think that point of contact, is it one point or one line or a surface? Actually, the teeth look something like this. Yeah? So if this is the radius, and then the teeth will come out. That would arc, straight, arc, arc, straight, arc. So the other side will be the same. So it cannot be a surface. What would it be? That point of contact. If you measure it, it will be just one line, because the other gear here, it will be also arc, straight, arc. Yeah? So arcing and arcing, when they touch each other, is one line. But even that one line, under high speed, it creates a lot of noise. Then mechanical engineers start to think, how can I then remove that noise and remove that amount of vibration if I want to rotate these two guys at very high speed. So they came up with this mechanism that's called a helical gear. So helical gear works in a very interesting way. So instead of this gear that are parallel to each other, what they did is to slant it. But yeah, it's actually hard to imagine. It's just kind of like right over there. What is happening over there is that if you were to slant it, what's going to happen is that when these two gear teeth were to mesh with each other, the contact point is actually only 1 point. Yeah. Some of you may be able to imagine it, some of you may not be able to imagine it. Any point that's being meshed is actually one contact point that will slide through the entire length of it. As it rotates. So there'll be that common mesh point, they will touch each other at one single point, and as it rotates, that single point would run through that entire length of that teeth. Hence, it's always one single contact point, very little friction, very little vibration, very little noise. Helical gear. And that's one problem. This helical gear, even that is sloping, is slanting, when it rotates against each other, it will rotate away from each other from the axis. That way. So when they rotate away from each other, then you have to apply some kind of spring or stopper system so that they can continue to be. If not, then they'll just rotate and then tend to move away from each other. That's because of the slope. Next year I'll buy that gear. So in order, I know you know what I mean. So in order to avoid this kind of sharp drift or helical gear, what they've done is come up with double helical gear system. So double helical gear, you can see that it's arranged in this chevron shape. So the chevron shape allows the compensation of this drifting from each other. So when you have this helical gear, double helical gear, next with another double helical gear, then these two gears will not drift away from each other. So I'll show you an animation. Sometimes called herringbone gear, or sometimes just double helical gear. So you can see it's just rotating. For any point of contact, it's only 1 point, and then you'll move through. Had it not been chevroned in that way, then if let's say just only this part, then these two gears are going to move away from each other. So if you have herringbone, that means it will stay over there, and hence your bearing system that's supporting it does not need to accommodate that axle loading. It's only that radial loading that's necessary, but not the axle loading. So we need to do some calculation for this helical gear, rim gear, especially when we talk about the gear ratio. Alright, so what I'm going to do is do a sketch just to give you some background to the terminologies that we use for something that's rotating. So if I have a disc that's rotating from that has rotated through this angle here, and the radius of that shaft is r. Any of this tangential velocity, I call it v. So v is a tangential velocity. And if you were to rotate in that way, then you would have this, what we call the omega is angular velocity. So if it rotates through from this radius position to this radius position, this arc length over there, S is actually the arc length, will be represented by S. So if I were to look at two gears, the pinion and the spur gear, and say that this pinion gear is rotating at omega A, angular velocity of omega A, and do you think the spur gear will be rotating clockwise or anti-clockwise? Gears, yeah, I didn't draw the gear teeth, but there are two gears, right? You gotta be anti-clockwise. Now, if you can't visualize this, I'll give you 2 packs of Lego toys that you can play with, and you'll be able to see how the gears mesh and rotate each other. So this one will rotate at another angular velocity that's called omega B. Now, so I call this A gear, and this one is B gear. B. So you can see that this common point over here, it will have both the tangential velocity that I call V. Now, you may know that tangential velocity is equal to radius multiplied by angular velocity. It's physics. It's a formula for calculation of tangential velocity. So I'm going to make use of this. V is equal to R A omega A, and since they share the same tangential velocity, this one must also be equal to R B omega B. So looking at these two right-hand side terms, I can do that cross multiply, so that omega A divided by omega B must be equal to R B over RA. This formula over here is written over here, omega A over omega B, and we call this our gear ratio. So if you take the radius of B divided by radius of A, you get the gear ratio. Or if you could measure the angular velocity, actually you can't. You can only calculate for your Lego lab. So had you been able to measure the angular velocity of A, divide that by angular velocity of B, that would similarly give you the angular gear ratio. So I know over here is a diameter of B divided by diameter of A. Actually, it's just like 2 times of radius of B divided by 2 times of radius of A. So you still get RB over RA, and so it's the same over here. What is not covered in your notes, actually we can prove that the number of teeth for B over number of teeth of A also will give you the gear ratio. There's a proof behind it, but I wouldn't spend time on that. So this N over there is number of teeth. Later on, we'll be using this N to represent our gear reduction ratio. So I'm not going to touch a lot on this so that you don't get confused with the other N, the same N, capital letter N that we'll be using. So that's for just 2 gears that are side by side to each other. If we start to look at gear trains, and gear trains is defined as a series of gears that are placed side by side to each other on different shafts. So you can see in this case, this one is a shaft, this is another shaft, this is another shaft. And these shafts are aligned close enough to each other such that the gears that are mounted on the shaft, they are rotating the other gears. So if you have a gear system that's arranged in this way, this one, the small one, usually we drive the small one. Some students actually wonder, why do we drive the small one? Can't we sometimes drive the big one? If you drive the big one, that means the smaller one will move faster or slower.
Faster.
Will move faster, right? In our world, usually we want to slow down things because your motor is already moving quite fast. So in order to make use of this rotation, in human scale, it's actually easier to use something that's rotating slower. But there's no slow rotating motor that doesn't require additional work, like maybe pulse width modulation control. All these would be costly. So we can use a simple gear ratio or gearing system in order to reduce the speed. So if this were to be rotating at certain speed, we know that the output of that, the driven gear over here, will be rotating slower. You can actually, some students also couldn't imagine why would this be slower. You can imagine this number of teeth over here. If you were to rotate one revolution, this part over here will only rotate probably around half that much because that gear tube needs to move and touch each other in that way. So if it's moving just half while this moves the whole revolution, that means this gear C will be moving slower. Right? So in that sense, gear reduction. Right? So this driver will sometimes certain textbook will say your input gear, and this one sometimes some textbook will say output gear. So we can try to prove this one as well. In this case, this center gear over here is not doing anything. It's just to make sure that your gear C is rotating in the same direction as your gear A. So we call it the idler gear. So let's formulate the equation. So this gear ratio is given as omega A over omega B, and omega C. And actually, this is the same as taking the gear ratio of omega A over omega B multiplied by omega B over omega C. So omega A over omega B is the gear ratio between this driver gear and the idler gear. Omega B over omega C is the gear ratio between the idler gear and the driven gear. So since they are connected in this gear train, so we can multiply them together in that way. So another way to look at it, we can start by looking at tangential velocity. R A omega A must be equal to R B omega B must be equal to R C omega C. So I can take between A and C and give this ratio omega A over omega C equal to RC over RA. So as the rest of it, I'll just establish between A and B. That will give me omega A over omega B equal to RB, RA. And then between B and C, omega B over omega C, RC, RB. So if I just look at this RC over RA, just this part over here, it's actually the same as RC over RB multiplied by RB over RA. So RC over RB, that is omega B over omega C. RB over RA, that is omega A over omega B. So this and this will cancel, so omega A over omega C. So again, you can see that this thing kind of like proves that your radius of your gear C over radius of your gear A is equal to radius, the angular velocity of A divided by angular velocity of C. So it's kind of like between radius and angular velocity, the gear is kind of like the other way around. Yeah? So if you want to remember it in that way, you can do that. So this thing is also equal to RC over RB. Sorry, RA. RC over RA. That is for gear trains. So if all these gears that are cascaded together, if they are sharing the same shaft, instead of, in this case, they are not sharing the same shaft, all of them are individual shafts. Once some of the gear shares the same shaft, then we call it compound gear trains. What's an example of that? This one over here is an example of it. So this one has got compound gear system because you can see that this shaft over here, which is this shaft. This shaft over here shares two gears in there. So when you have two gears here together, then we call it the compound gear train. If it's just one gear on each shaft, we call it the simple gear train. So let's have a look at how to get to that form. We have this gear A, B, C, and D over here. So we can establish the gear ratio G that's equal to omega A over omega D. That's equal to omega A over omega D. So between A and D, multiplied by omega D over omega C. So there's somewhat like a gear ratio between this omega D and omega C. The C is the one that's smaller over there. And multiplied by between C and D. So because omega B and omega C, they are on the same shaft, that means omega B and omega C are equal to each other. So this and this can cancel out. So whatever that's left, that gear ratio would be omega A over omega B multiplied by omega C over omega D. We can also derive another relationship. If I look at this radius, I call it RA, and that radius over here, I call it RB. This radius over here, RC, and that radius over there, RD. You can see pretty immediately, if I take RA plus RB, it must be equal to this RC plus RD. So this is also another relationship that you can get to help you to solve some unknowns if there are any. So if you're wondering, well, all this, a lot of mathematics, but what does it actually mean to me? Simple gear train and compound gear. What's the difference? It seems like a lot of calculation. If you look at for simple gear train, there's only one ratio, but for compound gear train, there are two ratios over there. So actually what compound gear train is trying to say is that if you require a lot of gear reduction, this is the one to go for, compound gear train, because it can afford you by having this gear ratio multiplied by the other gear ratio, and it's giving you a pretty large G value. A large G value means that when you rotate at a certain speed, it can be reduced to a very low velocity over at the treatment side. So you have a driver's side that rotates very fast, and then how to convert that fast revolution to a slower revolution. You have a compound gear train so that it can step down at a lower speed. So something that you can apply in your robotics lab. But that's one problem. Compound gear, even though it has got a very large gear ratio,
its problem is that being compound gear, it has a lot of gears that's inside. A lot of gears inside means that there's a chance of a failure because a lot more contact points over there. The entire compound gear box is going to be a lot more heavier as well. So these are some of the disadvantages
that you can find for compound gear. Is it here? No. It's mentioned over here, reduction gears. So although it can reduce the speed, it can also increase the torque at the same time. And later on, when we go to the topic of motor, that's when we talk a little bit about why reducing speed can increase the torque. So this compound gear, it increases cost because there are a lot more number of parts. It decreases reliability because there are more moving parts. Increase the weight and increase the moments of inertia. And there's this thing that's called backlash.
Now, the easiest way to talk about backlash is that if you have two gears that are meshed to each other, do you think it's always very tight fitting that you will rotate that way, or do you think there's going to be a little bit of free play? And whenever there's free play due to wear and tear, what's going to happen is that when you drive your driver gear, it's going to knock on it first before you will rotate. That knocking will cause even more wear and tear. And that is what we call the backlash of gear.
So typically for overall gear ratio, we keep it to be about 10 for a simple gear train. When you have compound gears, that's when we can go at a higher gear ratio. But for a simple gear train, usually it's just about 10. If it's larger than that, you'll be asked, why don't you go for compound gear? Because compound gear, very quickly, you can have a very large gear ratio. Okay. That's an example. So let's go for a quick break and then we'll look at that example.